There are two major equivalent ways to define sequential spectra. The traditional component-wise definition is what we cover here, and later we will introduce the second definition via topologically enriched functors, which will aid us in establishing the stable model structure. A sequential pre-spectrum, which is sometimes just called a sequential spectrum or even just a spectrum, is an object consisting of component spaces and structure maps. The component spaces are n-graded, and the structure maps tell us how to move between the component spaces. Keep in mind that the structure maps don't have to be homeomorphisms, but they can be, as we will soon see. Due to the suspension loop adjunction, we can equivalently define the structure maps with adjunct structure maps. So we have a sort of chain complex between the component spaces, in such a way that the maps between the component spaces factor through the suspension or hom space based on what type of structure map you're using. Homomorphisms are defined component-wise in the most natural way. There is a natural way to create an entire spectrum out of a single topological space, particularly compactly generated and pointed topological spaces. Its zeroth component is the space X, and we just keep suspending it to get the rest of the spaces. This is the special case I mentioned earlier of the structure maps being homeomorphisms. This is again just another way of saying that the nth component space is literally the n-fold suspension of the space. Formally, this idea of the entire spectrum being generated by a single space means that we have a functor, a quote-unquote infinite suspension functor, from the category of compactly generated pointed topological spaces to the category of sequential spectra on compactly generated topological spaces. Similarly, we could define infinite loop space functor. Of course, we could start with the single point, and we'd simply obtain all spheres, the standard sequential sphere spectrum, whose nth component space is the standard n-sphere. Like I said earlier, not every sequential spectrum is a suspension spectrum, i.e. not every spectrum's structure maps are homeomorphisms. It's not hard to believe that such spectra exist, but you might be wondering if such spectra are useful. A fundamental such example of spectra that are not simply suspension spectra are the real and complex tome spectra, which is a topic I hope to get to eventually. We'd like to start upgrading the homotopy theory from the category tope to this new category of sequential spectra. Let's start by upgrading our notions of smash products and mapping spaces, or internal homs. They are pretty much defined the way you would expect. The analog of the smash product here is called a smash tensoring, and on the component spaces it is just component-wise smash products. On the structure maps, it is the smash product of the original structure map with the identity function on K, which makes sense in light of how we define the new component spaces. The analog of the mapping space, or the internal hom, is called the powering of K into X. Its component spaces are the mapping spaces with underlying sets maps from K to Xn, and its structure maps are defined as you see here. To explain a little bit, I guess the first map is really the only ambiguous one. The first map sends points in S1 to the constant map from K to that point. Maps from K to Xn are sent to itself, the map from K to Xn. This map is called the constant identity map, which will make an appearance a little bit later. Again, these operations give us functors, which you see here. We've constructed these operations in such a way that certain things work out the way we'd expect them to. The smash tensoring of the standard sphere spectrum with the topological space X, for example, is isomorphic to the suspension spectrum of X. Let's return to this diagram from the introduction. This is where we want to be. Before we prove this diagram for model structures on these categories, we want to prove it without. The top adjunction here is just the classical smash hom adjunction, or the suspension looping adjunction. We turn right now to the bottom adjunction, so we want to prove that, and then afterwards we'll prove the vertical ones. So let's get that bottom adjunction. For now, not considering if it's equivalent adjunction, just considering the categories without a model structure. Here's the proof. To show that this is indeed an adjunction, we need to show that there's a bijection between the sets maps f and f tilde displayed here. So let's start with the function f. there's a homomorphism between spectra. So we have the following commuting square, or a set of these commuting squares. But by the classical smash-Hom adjunction in taupe, this is equivalently, or in other words, in bijection with commuting squares of this form. So the bottom map tilde fn plus 1 is what we want, but we also want the top map to have a tilde fn. As it stands, this is not what we have, but we can show that this is in bijection with maps of the form that we do want. This comes from the observation that the original top map S1 wedge Fn is the identity in the sense that, or is the identity in a sense on its S1 factor. The S1 always remained as a wedge factor, so it makes sense to try to split out the Fn and somehow apply the standard smash-Hom adjunction in such a way that only the Fn is changed into the tilde Fn. We can see that idea here, and using the constant identity map from earlier, this is indeed factors tilde S1 wedge Fn. Thus we have a bijection between those maps and maps tilde Fn, so we have a bijection between commuting squares. This displays the bijection and hence the adjunction that we are after. Now that we have that bottom adjunction, we turn to the vertical ones. To be clear on the notation, applying the infinite loop space functor to a spectrum acts as just picking out the first or zeroth indexed component space. Our idea is, of course, the same, to show a bijection between these maps f and tilde f displayed here. So f is a map from a suspension spectrum to some other spectrum y. Again, we can see this as a set of commuting squares. But since we are working with a suspension spectrum on the left vertical map is actually an isomorphism, or rather a homeomorphism. What this means is that the two horizontal maps are related. Specifically, fn plus 1 is entirely determined by the map fn. So considering all such fn, we see that all of them or all of f is determined by that initial map f0 from x to y0, just going backwards further and further, all the way to f0. But remember, y0 is just the infinite loop space functor applied to y. Every map f0 and by extension f thusly corresponds to a map f tilde from x to the infinite loop space functor applied to y. This exhibits the bijection we are after, and hence the adjunction.